This lecture covers hypothesis testing for a one-sample study. It is in Module 2, Comparing Outcomes. Let's look at hypothesis testing in the context of the first study example. In our first example, we are interested in knowing if high school students are sleep deprived. The authors of this paper define enough sleep as 9 hours per night. When we write the hypotheses, the null hypothesis is constructed to assume that the null parameter is the true parameter. To determine if high school students are sleep deprived, we start by assuming that they get enough sleep. Therefore, the null hypothesis is that the true mean sleep hours for high school students is 9 hours. We can also write this as mu equals 9. We are interested in if high school students are sleep deprived, meaning that they get less sleep than they should. Therefore, the research hypothesis is that the true mean sleep hours for high school students is less than 9 hours. We can also write this as mu is less than 9. We are dealing with a one-sided research hypothesis because we are only interested in if students are sleep deprived. If they get more than 9 hours of sleep, they are not sleep deprived. Just as a confidence interval has a specific format, a test statistic will always have the same basic format. Statistic minus null parameter divided by standard error. In this case, our statistic is x bar, the sample mean. The null parameter is mu0, the value from the null hypothesis or the null parameter, and the standard error is s divided by the square root of n, or the sample standard deviation divided by the square root of the sample size. We know the sample mean, the standard deviation, and the sample size from the summaries lecture. We know our null parameter from the previous slide, 9 hours. However, before we plug in these values to calculate the test statistic, let's talk a little bit about the format of the test statistic. The test statistic is denoted by t. In the numerator, the null parameter is subtracted from the sample mean. This picks up the null distribution and shifts it horizontally so that it is now centered at 0. Dividing this value by the standard error standardizes our result so that we have comparable units. Let's look at this visually. On the left is the original sampling distribution of the mean, assuming that the null hypothesis is true. 0 is a possible statistic, though unlikely, and so it is on the x-axis of our sampling distribution. On the right is the sampling distribution of the mean minus the null parameter. It is now centered at 0. Dividing by the standard error gives us a known usable unit of distance. For example, if I asked you to report how far away something was and you told me 3, what do you mean? 3 inches? 3 miles? 3 meters? Without units, distances are difficult to understand. The standard error is a unit of distance on a sampling distribution. Once our statistic is centered and standardized, we can use well-known distributions to find the corresponding p-value. Now let's calculate the test statistic. I recommend using Excel, especially the cell referencing capabilities, to do this calculation. Remember to use lots of parentheses and to follow the order of operations. Please pause this video while you make this calculation. In Excel, I can select an empty box and type equals and then the formula shown on the slide. I will use cell referencing by clicking on the boxes where each value is contained. When I hit enter, we will see that the test statistic is negative 75.09. Note that a negative number is good. Our research hypothesis is less than, and 0 is now the center of our distribution, so the test statistic should be less than 0, which will be a negative number. To find the p-value, we will use Excel. Note that there are 3 Excel commands for finding a p-value depending on the research hypothesis. T.dist is used when the research hypothesis is less than. T.dist.rt is used when the research hypothesis is greater than. And T.dist.2t is used when the research hypothesis is not equal to. All 3 functions are formatted the same basic way, though only T.dist includes the cumulative statement, which is always set to true. The arguments are x, the test statistic, degrees of freedom, which is the sample size minus 1 for a one-sample study, and cumulative, which is always set to true. We can type this into Excel to find the p-value. Excel returns the value of 0. Though our p-value is never actually 0, in this case it is small enough that Excel says it's basically 0. This is because the test statistic is very small. In this example, anything less than about -2 is going to be significant, so -75 gives us a very, very small p-value, so small that Excel says it is essentially 0. Remember that the p-value is the proportion or percent of less expected statistics. If the p-value is less than the significance level, then we have enough evidence to reject the null hypothesis. Otherwise, there's not enough evidence and the null hypothesis is not rejected. Please pause this video now and determine whether 0, the p-value, is greater than or less than the significance level of 0.05. The p-value is essentially 0, which is much less than 0.05. Because of this, we reject the null hypothesis. This is what we call the decision. Just as the confidence interval is interpreted, a hypothesis test has an interpretation or a conclusion. This will always follow a specific format, whether there is or is not enough evidence, plus the research hypothesis. In this case, since the null hypothesis was rejected, we say there is enough evidence to conclude that the true mean sleep hours for high school students is less than 9 hours. One of our assumptions for using a t-test is that the outcome, sleep hours, is normally distributed. However, this may not always be true. In this case, we would have to use what's called a non-parametric test. The only assumption of a non-parametric rank-based test is that the data have order. Since our outcome is continuous, it does have a natural order to it. The associated non-parametric test for a one-sample t-test is what's called the Wilcoxon signed rank test. This uses the median as a measure of center instead of the mean, as the median is a better measure of center than the mean when the outcome isn't normally distributed. More information is provided in the textbooks on the listed pages. Now let's look at the second study example. Remember in this example that we're comparing the usefulness of an iPhone app to the usefulness of the photo tracing method for preoperative assessment of surgery. Looking at the data in Excel, column D contains the difference in scores for the iPhone app minus the photo. If the scores are the same, the difference will be 0. Therefore, our null parameter is 0 because we assume that there's no difference between the two methods or that the scores are the same. We can also write this as mu d is equal to 0, where the d means difference. If our goal is for the iPhone app to be more useful than the current method, what do you think our research hypothesis should be? Please pause this video and determine whether the research hypothesis should be less than, greater than, or not equal to 0. Remember your selection. There will be a quiz question related to this example. The test statistic for a paired difference study is exactly the same as a test statistic for a historical control study. The only difference is that the sample mean and standard deviation are subscripted with the letter D to denote that the mean and standard deviation are of the difference in values or scores. In Concept Practice 4, you will calculate the test statistic and p-value for the test of the true difference in scores from the second study example.